Mechatronics systems. And generally people use these terminologies for reliability, safety, performability interchangeably, but it has a very clear demarcation. And we need to understand what each and every terminology mean. And these are the attributes of the dependability, which is a non-functional attributes. Yesterday we had discussed about the dependability attributes, why it is so important, especially if we are dealing with the safety critical systems. So when you look or analyze any system with respect to safety, you try to identify what are the risks associated. So first thing is you have to identify the risk that can be associated with your system throughout the operational life. And the second one is you have to devise the mitigation techniques of those risks so that you can ensure even if such risk exists, how you will be able to mitigate those risks. So you can quantify the safety with by defining the risk, and risk can be defined as a probability of occurrence of any event into the frequency of that event, the frequency of occurring of that event. So now here we will be talking on reliability, and the reliability of the system can be defined as probability of the system, probability of the failure-free operation of the system up to a given period of time under certain environmental conditions. Now, when I say probability of the failure-free operation of the system, it means it is denoting the probability of the success of the system, and up to given period of time. That is very important. So the definition is each and every term is very important. Whenever I talk of the reliability of any particular component, system, even human reliability, I have to talk up to what period of time I'm talking. What is the target time? Because if you can remember your childhood days, you may be having a lot of friends in your childhood where you must be at that time you would be thinking like these friends are going to be forever in my life. But as and when the situation changes or the dynamics changes, you start welcoming new friends and they start taking the place of old friends. So what I mean to say, if you talk about the reliability, you'll have to talk up to what period of time you are talking about, because nothing can be reliable for infinite period of time. So it means reliability is a function of time. And the second one in the definition, I brought out the fact that it depends on the certain environmental conditions. Yes, it may happen that one thing may be reliable, maybe more reliable under one operating conditions and maybe less reliable under different operating conditions. For example, if you go and purchase a refrigerator and you get a warranty period of 1 year, but if you come back to your home with this refrigerator and probably you throw that refrigerator from say 14-story building, it will collapse. And you cannot go back to the vendor and say, look, you have given the warranty period of 1 year. I want the replacement of this refrigerator. So what he will say, what the vendor will say to you, look, you have not met the operating conditions under which it was supposed to be operated, and hence your warranty has been voided. So one thing I want to conclude here is that reliability depends on the time, which is the target time, and the second one is the operating conditions, under which operating conditions you are operating your product. And we'll see the quick agenda of today's talk. So introduction of to reliability and background that I have already given. I'll not be wasting much time on it. Probably we can discuss some of the traditional techniques or methods through which we can, quantify the reliability. Then again, I'll be touching on the Petri nets and the modeling of the systems. Yesterday, we have seen what Petri nets are and those and how the Petri nets will be able to uh, address the safety issues or how we can perform the safety analysis of the system using Petri nets. In this session, we will see like how we can use the Petri nets for the reliability quantification. We have to quantify the reliability. We'll see like what are the various properties of the Petri nets, what are the analysis techniques, and then I will propose a reliability prediction framework in which I'll be discussing the various steps or various phases that needs to be executed for the quantification of the reliability of the particular system. And then I can conclude my session. Let us see the mathematical definition of the reliability. So suppose X be a random variable and that represents the time to failure of a component. So it means if your component fails before this time, it is the failure of the component. So this represents the target time. So the reliability of the component at time t can be given by Rxt, where because as I said, reliability is a function of time. It will be equal to the probability that the value of x is greater than t, because it represents a success probability, and success probability will only be when this random variable value will be greater than your target, time, because it is representing the time to failure. So this time to failure must always greater than your target time. It means at least it means I'm guaranteeing that up to this t time my component is working, and this can be equated as 1 minus, from the probability theory, 1 minus p x is less than is equal to t, and where px is less than is equal to t represents the probability of the failure because it has failed before time t, and hence we can write it down as a failure probability. So it will be equal to 1 minus failure probability, which is also a function of time. So reliability is equal to 1 minus failure probability, and failure probability we sometimes say it is as unreliability. So reliability is equal to 1 minus unreliability. And because it is a probability, so its value ranges from 0 to 1. 0 means least reliable and 1 means highly reliable. Now let us see some of the traditional methods that were used for the quantification of the reliability of some systems. So one of the prominent model that is known as the reliability block diagram, and it represents the logical structure of the system with regard to how the reliability of its components affect the system reliability. So for example, how it works like, suppose you are having component and you are having a system in which only two components are there. Let it is R1 and R2, having the reliability R1 and R2 of those individual components. Then the reliability of the overall system will be equal to R1 into R2 if they are arranged in the series, or if the components are arranged in the parallel, you can use the parallel reliability formula. And in this way, you can solve the entire system to come out with the reliability of the overall system. So the main concept is, if you are able to have the or assign the reliability of the basic components, you are able to know the architecture of your system. What is the arrangement of those components, whether they are arranged in the series or parallel or in combination, then you will be able to solve the reliability of the overall system. Now the next prominent model is known as reliability graph. And if you talk about the basic building block of reliability graph, it consists of a set of nodes and edges, where nodes are used to model the link between two components, and arcs are used to represent the components in the system. So for example, if you are able to see this figure, the left figure is representing the reliability graph, where A, B, C, D, these are the connectors, because these are the vertex, and the edges, which are represented by V1, V2 up to V5, these are the components itself. And we can equivalently transform into the reliability block diagram, which is shown in the right side. So as I said, all these V's are the component itself. So I have replaced V1 by component 1, V2 by component 2, likewise. And all these vertex are the connectors, so which I'm using to represent the connectors between the components. And now I can solve this reliability block diagram. For example, the 2 and 5 are in series. And if they are having the reliability R2 and R5, so the reliability of this block or this branch will be R2 into R5. Similarly, reliability of 1 and 4 block will be R1 into R4. And all these will be then in parallel. We can use the parallel reliability formula. So in this way, we can calculate the reliability of the overall system. The next method, which is mainly used in all the mechanical industries and electronic industries, are the fault tree. And fault tree basically represent all the sequences of individual component failures that can cause the system to stop functioning. And it is like a tree structure. So, for example, let me try to explain. Suppose your laptop is not working. So the top failure event is my laptop is not working. And now I want to know the reliability of your laptop. So how I can do? I will try to deduce the root causes of that particular event. For example, laptop is not working, then the reason could be either power supply failure. So that is one reason. Then, so this is one event rather. The other event could be some electronic failure. That is a second event. The third event could be mechanical failure. That is a third event. So, and these three events are in OR logic, because if anything is fail, my laptop is fail. Now coming to the power supply failure, I will further deduce what are the root causes till I reach to the basic event. And so I can figure out, how your power supply, how you will declare as a fail. Because you are not getting power supply in the laptop. And what could be the reason? Either the power is not coming at all, or either your particular switch is not working properly, or either there is a loose connection in the plug and the socket, Either there is a loose connection from the laptop connector side. There could be wire break in between. There could be so many reasons. So, and if the root causes are, basic root causes are in OR logic, we can, then we have to assign the probabilities, irrespective of they are in AND logic or OR logic. So once I reach to the basic event, I need to assign the probability of those basic event. And those basic event probability I can assign from the various sources. For example, in the electronic component, you can see the mill handbook, which gives the probability of the failure of various kind of registers, electronic components, and so many other things. Similarly, the mechanical components catalog is there. That is publicly available, from where I can assign the root causes, assign the failure probability of the basic events. Or we can even use your experience, operating experience. And once I assign the probability of the failure of the basic events, then I'll have to see whether those basic events are in OR logic or are in AND logic. If they are in OR logic, for example, the failure of the B fails because of failure of A and failure of C, and A and C are the root causes, are the basic events, and the probability of A and C failure are PA and PC respectively, and they are arranged in OR logic. Then the failure of A, the top event failure will be the addition of the probability of the failure of the basic events. Okay, so top level will be the PB plus PC. And if they are arranged in the AND logic, then we have to multiply the probabilities. So in this way, we can keep on deducing till we reach to the top level probability, which defines the failure probability. And we have already seen that reliability is equal to 1 minus failure probability. So if we can subtract this failure probability by 1, then we can quantify the reliability of that particular system. So in this way, we can quantify. Now, the models that we have seen so far, definitely they can be solved using fast algorithms. But they assume the stochastic independence between the system components. And they assume like the components in the system, if any component fail, only it is responsible and it is an independent failure. But no, when we deal with the stochastic processes, basically one component may fail because of the another component, because of the getting the wrong input from the other component. So there is some stochastic dependence between the system components, and it is essentially to include that stochastic dependence between all the system components. And we want to have a model where I can model the complicated interactions between the components. And the existing models or the traditional models that we have looked so far are not capable to model such kind of stochastic behavior. And hence we must use some other kind of models. And that includes, the Markov chain or the Petri nets. Petri nets we have seen yesterday also, but today also I'll be covering the working mechanism, because our entire method will be depending on the Petri net model. So if you look into the Markov models, The concept was introduced by Andrew Markov in 1940s, and who was a Russian mathematician. And he also introduces this concept to model the stochastic behavior of the system. And the idea that he thought of, like any system can be decomposed into the various states. And definitely one a system can transit from one state to another state with some probability, with some transition probability. And that depends on my statistical data or on my behavior of the system. For example, suppose there is a human being, and if you uh, talk about the possible number of states that a human being can confront, that may include sleeping, talking, running, walking, laughing. And these states are, the behavioral states. But there could be the failure state if suppose any human being is meeting an accident or he is sick, it's a failure state. Then you have to identify what is the probability that your system is in the behavioral states, and behavioral states means success state. And you can sum up all those probabilities to give the quantification figure of the reliability. Or otherwise, because the behavioral states are many and the failure states are less, the other way out is you can sum up all the probability of the failure states, and you can subtract that probability by 1, which can give the quantification of the reliability. Right? So if you see, let us try to understand some of the mathematical concepts related to the Markov chain, which we'll be using in our method. So suppose there is one system which is having only 2 states, let us say I and j. And or suppose let us say we are having n number of states, and ij is belong to that sample space, that state space. Then let qij be the transition rate from state I to j. Then the transition rate from that state to the same state will be equal to minus, and we have to sum all the transition rate from that state to rest of the states. Okay, so this formula is very important that we are going to be using in our quantification method. Then let us define one term known as generator matrix or transition matrix. And as it is a matrix, so it is a collection of rows and columns, and where you can write all the states in rows and columns, and you can fill in the elements with the transition rates from one state to rest of all the states. And that matrix is known as transition matrix or transition rate matrix or generator matrix. Okay, so these two terms you will be using in our method. Now coming to the PatriNet, yesterday, although we have talked about the PatriNet, but still I want to reiterate because our entire approach is based on this. So PatriNet, as we have seen, it is a graphical and mathematical tool. And why graphical? Because it gives a visual communication aid, and you can represent, you can simulate the behavior of the system in terms of modeling construct, and which you can show to all the stakeholders, and they can easily understand the behavior of that particular system, and it can help also to all the stakeholders. For example, there is a tester, he can figure out like what could be the behavior of that system during runtime, and it will help him to design some of the test cases, important test cases, to test the system. And it is also a mathematical tool. So yesterday we had only seen the modeling aspect. Today we will see like how the mathematical equations can be derived from this model, and those mathematical equations can give a lot of insights about the system. So particularly in this session, we will be talking about the reliability quantification. And as I said, so if you see the history, the same as I shown yesterday. So the concept was introduced by C.A. Petri, who was a German PhD scholar, and he introduced this concept in 1962 to represent the stochastic behavior of the system. And we had already seen yesterday the process can be categorized into the stochastic processes and deterministic processes. And deterministic processes are those processes whose outcomes can be 100% guaranteed, whereas the stochastic processes are those processes whose outcomes cannot be 100% guaranteed. So after, reviewing his thesis or going through the thesis, the people were trying to put or to explore whether this modeling concept will be able to model the concurrent and parallel systems. And with this objective, in 1970, MIT USA conducted a MEC conference on concurrent systems and parallel computation. And the conclusions were very fruitful, where the people were more eager to know more and more potential to strengthen the model to solve more and more complex or challenging industrial problems. And with this objective, again, they decided to meet after 5 years. So where again, MIT USA conducted a conference on factory nets and related. And because of, gradually its demand started increasing in the industries, and industries wanted the person or the people who should have at least the basic modeling knowledge of this factory net. And to meet this demand, looking at the demand, Germany started a course on general net theory of processes and systems. And in after that, the people from the different domain, they start thinking or exploring this modeling construct, whether it can be used for their specific domain. And with this objective, we decided to meet. And the first European workshop on applications and theory of the factory net was conducted in France. And then the different flavor of factory net also started coming up. For example, if I want to work on the real-time system, a specialized factory net known as timed factory net was introduced, for which the first international workshop was conducted in 1985 in Italy. And so this is just, it's not a exhaustive list, but it is just some of the milestone, which basically shows how the factory net became so popular and the motivation of this study. And applications, as we said, as we have discussed yesterday, it is basically used in almost every kind of application. And now I'll be talking on the working principle. Although I have discussed yesterday, but I was very quick. And so because for easy grasp, I have taken the same example, which I have taken yesterday. So that whenever I'll be discussing the case study, you can easily understand the working mechanism of that case study using this battery net. So suppose I want to model a very basic chemical reaction, that is 2H2 plus O2, that gives 2H2. And so before directly going to the model of this equation using battery net, let us try to understand what are the basic constructs of the battery nets. And if you are able to see this figure, you can see there are the three big circles. And these three big circles are known as places. And I'm using these places to represent hydrogen, oxygen, and water. So I have used the three places. Then the second modeling construct is known as transition, which is representing which is represented with a rectangular bar. And here in this figure, there is only one transition. And the places can be connected with the transition, and transition can be connected with the places. But there cannot be a direct connection between the places and between the transition. Now the next is so these connections can be taken by the help of a directed arc. And the next building block is the weight of the arc, which is defined by the, or which can be shown by putting a numeric number on that particular arrow. So if you see in this figure, the arc which is connecting hydrogen place and transition T is having weight 2. And the arc which is connecting oxygen place and transition T is having weight 1. I have not put any number, so either I can put 1 or I can leave it like this. It will be treated as weight 1. Similarly, the weight of the arc which is connecting transition T and water is 2. Now, one more important building block, you are able to see the small or the embedded tokens inside the places. So the hydrogen place contains the 2 tokens. These are the small embedded circles inside the places known as tokens. So I am representing these tokens. For example, in hydrogen place, I am representing the tokens in the hydrogen place to represent how many atoms hydrogen you have, which is 2. Similarly, for hydrogen, for oxygen place, I have used 2 tokens to represent the 2 atoms of the oxygen. And the distribution of the tokens basically represent the state of the system. So for example, in this figure, the distribution of the token is 220. So 220 represents the state of that system. Now, so this state is basically representing the left hand side of this equation. And now it has to be converted into the water, and hence the state of this system needs to be changed. And because the state is represented by the distribution of the tokens, so we need to change the distribution of the tokens. But there is one rule by which we can change the distribution of the token, And the rule says that in the Petronian figure, at least one transition must be in enabled state. So in this figure, there is only one transition T and it must be in enabled state. But what is the enabling criteria of transition? The enabling criteria of transition is that all the input places must contain sufficient number of tokens. And all the input places for this transition, for example, in this figure, the input places are hydrogen and oxygen because those are connected with the input arms. And the output place is water because it is connecting by output arm. So hydrogen and oxygen must contain sufficient number of tokens for the enabling of this transition T. But who will decide the sufficiency of the tokens? The weight of the respective arc will decide the sufficiency of the token. For example, in this figure, the weight of the arc which is connecting hydrogen place and transition T is 2. So, hydrogen place must contain at least 2 number of tokens. At least for the enablement of the transition T. But and oxygen must also contain sufficient number of tokens. And what is the sufficiency criteria for this oxygen place? That is 1 because the weight of the arc which is connecting oxygen place and transition T is 1. So the oxygen place also contain only 1 number of tokens. So it means this transition is enabled, and hence the token moves from input places to output places. But how many tokens will be moved out from the input places and how many will be deposited to output place? That will depend on the weight of the respective arcs. And in this figure, the weight of the arc. So weight of the arc is 2, which is connecting the hydrogen place and transition T. So after firing 3, because if any transition is an enabled condition, it fires. So after firing T, the 2 tokens will be moved out from the hydrogen place and 1 token will be moved out from the oxygen place because the weight of the arc that is connecting oxygen place and transition T is 1. So in total, the 3 tokens will be moving out from the input place. But how many will be deposited in the output place? And that also depends on the weight of the output arc. And here the weight of the output arc is 2. So only 2 tokens will be deposited in the water place. So one noticeable fact that I can bring out is that there is no law of conservation of tokens. The movement of the token depends on the weight of the arc associated. For example, in this figure, the 3 tokens has been moved out, but 2 tokens will be deposited. So the next state, which has been converted into water, is 0, 1, 2, because distribution of the token is now 0, 1, and 2, and which represent the state of the system. And now, if you see this figure, this transition is in a stable. This transition is in dead state. Now it cannot be enabled because the input place hydrogen is not containing sufficient number of tokens. So, so it means it only contains the two states. So it also helps in identification of the number of states that are possible in your system. And here I want to introduce a concept of reachability graph. And reachability graph is nothing but it represents a graphical, it represents all the states of the system in a tree-like structure or in a graph-like structure. So if you see this system, the first state was 220, and after transition T, the state has become 012. Now let us see some of the mathematical concept of the Markov chain, which we were talking about, and the representation of the Markov chain can be seen by this figure, where I have shown that on a system contains only two states, S1 and S2, and it can transit from S1 to S2 and S2 to S1. And states are represented by the circles, and transitions are represented by the arc. So mathematically, the if I talk about the property of the Markov chain, the current state will only depend on the previous state and not on the past state. Or the next state will only depend on the current state and not on the previous state. So how we can represent it mathematically? If there is a sequence of random variable, x1, x2, x3, and so on, then what Markov property says that probability that x is that my system is in n plus state, n plus 1 state. If it is x, it will only depend that what is the probability that what is the probability of my system be in state x and x at x, and it will not depend on the previous states. So it can be written as Pxn plus 1 is equal to x, given xn is equal to x. Now this slide represents a random example of the reachability graph. So suppose there is a random Patrinet figure which contains 7 places and having the tokens like this 1 0 0 1 0 1 0, and this is representing the state. Sometimes the state are also known as marking, so I'm representing it by M1. And after transition T1, suppose the distribution of the token changed to this, which is the next marking or next state. Then further, after transition T2, like this. It is just a random example. And because it is representing the state, so this reachability graph can be converted into the Markov chain, which is represented in the right hand side. And this is M1, M2, and 3, M4 are nothing but these are the states. And the transitions, these lambdas, all the lambdas are known as the transition rate. Now let us try to understand the reliability prediction framework. And which contains basically 3 phases. And in the how to quantify the reliability. And in the first phase, I have to create the Patrinet model. In the second, I'll have to convert it into the Markov chain. And the third, I'll have to compute the reliability. And we have already seen how we can create a Patrinet model. Although when we'll be taking a new case study, we'll be demonstrating how we can create the Patrinet model again. And then we can definitely convert it into the Markov chain by first converting it to the reachability graph, and therefore that reachability graph can be directly converted to the Markov chain, as we have seen in the previous slides. And then we can use some of the mathematical knowledge to quantify the reliability. So first and two we have already discussed. But before taking the case study, let us try to build some of the mathematical fundamentals which we are going to use in our approach. So suppose let pi I(t) be the probability that a component is in the state I at time t, where I can be failure states or behavioral states that we have already discussed. And then if t goes to infinity, these probabilities converge to a stationary distribution. It is very important to understand the meaning of this state. It says, like, when it takes a longer time for a system, it converts to the stationary distribution, or it converts to the stability. For example, suppose you do have a glass, fill it with water, and you put it down on the table. You will find at the initial time the water was zigzagging, but after some period of time it will become stationary. But just try to replace the glass with a huge container, probably at the size of the room, and you fill it this water and you lift that container and put it down somewhere, you will find that it will take a very, very long time as compared to it was taken in the glass to settle down that water or to converge into the stationary distribution. So what I want to bring out a fact, when your system is more complex in nature, it takes longer time to converge to the stationary distribution. And this is, so which can be computed by the two equations. One is very simple, that represent like the probability, the sum of the probability of a system being in all the states at a time is equal to 1. That is from the total probability law. That is very simple. Let us try to understand the second equation. What does it mean? So consider the same example of the big container where you were filled with the water. And you can say, like, initially the water was very zigzagging, and let us denote it like it is an state S1. Then after some period of time, for example, after delta t time, it is propagating towards the settling process. And for example, after delta t, the state changes from S1 to S2. Then definitely S2 will depend on the S1 and the transition probability from S1 to S2. Now further from state 2, after delta t time, it is again propagating towards more settling process. And let it reaches at state S3. Then S3 is equal to S2 into the transition probability from S2 to S3. And the process continues till it reach the final state Sn. Final state means now the state is not changing. And suppose at Sn, your water is settled. Then what will be the next state? Sn plus 1. Definitely the equation will remain same. Sn plus 1 is equal to Sn into the transition probability from Sn to Sn plus 1. But Sn plus 1 is equal to Sn only, because the state is not changing now. And this is what this stationary equation means. That pi estimator, it is equal to it. So it is the stationary probability. It is equal to the same into the transition probability matrix, because we are dealing with the multiple states. So we are putting the entire matrix. Okay. So these two equations are very important, which we'll be using in our approach. And now let us try to understand the case study of a communication module. And the system architecture is like this. You do have two embedded units. Suppose, for example, you do have one embedded unit, and that is getting the data from the field sensors, and that is then transfer the data to the graphical user interface or to some display unit. And the connection is TCP/IP based. So if you look into the protocol, because I'm more interested quantifying the reliability of the communication module. So before that, let us try to understand the algorithm of this module. An algorithm is very much similar to, like, when I want to make a call to my friend. I just pick my mobile, I dial his number, and I say hello. Well, after ringing and after he picks up. And then I say hello and I wait for the acknowledgement. If I don't get the acknowledgement for some period of time, I again say hello. And this process I will continue to repeat till I get some acknowledgement from my friend. But up to what period of time I should wait? I cannot wait for the infinite period of time. After some designated time interval, I don't receive the acknowledgement, then what will I do? I will cut the call and I will retry. And the similar algorithm is basically implemented here. So when the embedded unit sends a new packet, because the data is transferred in the form of packets, so we are keeping one variable count that is set to 1, just to trace how many packets have been sent. Then embedded unit waits for the acknowledgement for T1 time after sending the packet. And if embedded unit receives acknowledgement before T1, packet send is declared as successful, and a semaphore variable I have kept, I will change it to its complement. And if the count is less than n and the acknowledgement is not being received, then embedded unit have to retransmit the packet, and it will keep on increasing the count till n. Otherwise, if it will become equal to n, the embedded unit terminates the send process unsuccessfully, where the semaphore variable will not change. And after T1 elapsed after the last data send, the semaphore variable will be destroyed. And now this algorithm, now let us try to create, to construct a Patrinet model of this algorithm. So this is a Patrinet model. Let me explain each of the places and transitions. And again, like all the transitions have wait 1. So the PSRDY, this place, if there is a token in this place, it represents that embedded unit is ready to send the packet with semaphore variable is equal to 0. And I have initially put one token at one more place that is known as PDSR, which represents that embedded unit gets the request from display unit to send the data. And there is a transition TS0, which represents that embedded unit sends the packet with sequence number 0. And it said that a try count k is equal to 1 by firing the transition. Then PSW0, it represents that This place represents that embedded unit is waiting for acknowledgement with sequence number 0. Because once I have sent, it has to wait for the acknowledgement. And then TSW0 transition, it represents that the embedded unit detects the timeout of the acknowledgement. And when it will be timed out, the token will be deposited to BT0N0. And hence it has to retry with the same sequence number because the timeout is there and no acknowledgement was received. So one trigger TS0K, it triggers like embedded unit sends the packet with sequence number 0, and this transition is fired only when K is less than N. And subsequently, the K increases. And if it succeeds to send the packet, the token will be in TS0S. And then TCOM1 represents that the display unit sends the acknowledgement to the embedded unit with the sequence number 0. So if there is a token in this place, PR1R, it represents that acknowledgement with sequence number 0 has received. And if it is received, then the token will be pulled out from the waiting place where it was waiting for the acknowledgement, and it has to report that the data has been sent successful, which can be reported to the operator, and again it will be ready for sending the new package. Or otherwise, if it becomes after timeout, if it is not packet send is unsuccessful, it will trigger this transition that is TS0 acknowledgement unsuccessful. And after that, the token will be deposited on in PTSAU, which represent a data send unsuccessful. Now, one interesting fact that we can see from this figure, the left part of this figure, left half of this figure is mirror image of the right half of the image. That is why, because for the redundancy purpose, we have taken the two embedded units. And for the online testability feature, I'm sending the package alternatively by alternate embedded unit so that I can assure all the times that both the embedded unit are healthy, and there is no need to test any embedded unit explicitly. So the right side working is also the same, that is applicable for the second embedded unit. And after that, after modeling, we have to assign the model parameter in which we have to assign the transition delay, the delay period of the transition, and it can be derived from various sources and knowledge, and by using the artificial intelligence also from the similar kind of project. For example, we can use the Bayesian update mechanism to understand the prior transition delays from the similar kind of projects and the new observation data, and we can keep on updating. And this is the transition delay. It is in the milliseconds, which we can assign, and we can use, because this battery net is a big, we can use the tools. There are several tools available to analyze the battery net. So after using the tool, we can quantify the throughput of each of the transition. Throughput means firing rate of each of the transition. Firing rate means number of transitions per unit time. And from the TimeNet tool which we have used, the values are given, are the values obtained are listed here. And once I have created some Mechatronics model, I have to convert it into the Markov chain, for which I'll have to create the reachability graph. And for the reachability graph, I have to see what all the possible states and which is represented by the distribution of the token. So you can see at the initial time, the distribution of the token is just one. There are the token only in two places, and rest of all are not having tokens. So you can write this is the marking or a state 100001000. These only two places are having one tokens. Similarly, you can see in this figure TS0 is enabled state because all the input places is having sufficient number of tokens. And from these two tokens, the token will it will be moved out and will be deposited to the places PS0S and PSWG. And hence you can see the next state is from the original places the tokens has been moved out and distributed and deposited into the other two places. And we continue this process till we cover up the entire state space of that system. And this marking or state are known as tangible if you have associated some delay with the transition. If you don't associate any delay with the transition, those transitions are known as immediate transitions, and where the markings will be vanishable marking. And just for the convenience, I have mapped all these throughputs. Lambda is 0, lambda is 1 to 1 to lambda 1 to 3, and so on, just for the writing convenience. And this is the reachability graph, the left figure, where all the markings and which are the responsible transitions that is leading from one state to another state are stated. And interestingly, you can see there are the two markings M3 and M8, which are basically failure states because these states are led by the transition, by firing of the transition of unsuccessful acknowledgement. So what I can do, I can find out the probability of these two, these two states, and I can add those probabilities and I can subtract by one, compute the reliability of the entire communication system. So this anyway, we will see how we can do that. But next we have to convert this reachability graph into the Markov chain, and this is the Markov chain where these states we have just represented it by the circuits, and all these transitions are having the transition rates which are represented by the lambdas, and which are nothing but which are all these lambdas. And now we have to create the transition rate matrix, which we have discussed already, which contains the rows and columns. The rows where the states, all the states can be listed out, and we can have to fill in all the elements of the transition rate. So all the lambdas we can fill in. So you can see, for example, in this figure, from M0, it can transit to M1 with lambda 1. So you can write from M0 to M1 with lambda 1 transition rate. And the self transition rate will always be minus summation of this, as we have seen in the first equation. Similarly, the rest of the matrix elements can be filled in. And now, so this is a transition rate matrix. And we have to convert this transition rate matrix into the transition probability estimation. And which is very simple. If I, for example, if I want to calculate the probability from state I to state J, it can be equated as a transition rate from I to J, and we have to normalize this transition rate. And for the normalization, I'll have to sum up all the transition rates from I to rest of the states. So this is applicable if J is not equal to I, otherwise it is 0. And hence we can derive the transition probability matrix. So from the transition rate matrix, we can derive the transition probability matrix. And now we have to utilize those two equations. I'm going back to those particular slides which we were discussing. And the first equation, as I said, it is a summation of all the states is equal to 1. Probability of a system being in all the states. So M0 plus M1 plus M2 up to M9 will be equal to 1. And the second equation is nothing but we have written it is here. So this is the stationary, state probability M0 to M9. It will is equal to same. And we have to multiply it by the transition probability matrix. And after solving these equations, we can come up with the probability of a system being in all the states. And as we said, the two states are failure states, that is M3 and M8. So what I can do, I can add M3 and M8 probability and I can subtract it by 1. And you can see the reliability of the communication module that comes is 0.99603, and which is a very good fact. So, here we have seen how we can quantify the reliability of the system, and we have seen like how we can utilize a battery net, and our phases contains mainly 3 phases. First, we have to create the battery net model, and you'll have to convert it into the reachability graph where you can identify all the possible number of states or the total state space of the system. And then you have to apply the mathematical knowledge to come out with the probabilities of the failure or all the success states. Then either you can sum up all the success state probability, which can give the quantification of the reliability, or if your success states are more, you can sum up all the failure state probability and you can subtract it by 1. That will give the quantification figure of the reliability of that particular system. So that's all I wanted to share. In case of any questions, I'll be happy to answer.
Yeah, participants, you can ask questions now. Okay. Okay, sir. Then thank you for Lalit, sir.
Yeah.
Yeah, thank you for your nice lecture on how you have explained how you can able to calculate the reliability of the systems and the embedded systems and the mechatronic systems, and it will be very useful point of view. Okay. So thank you once again, sir, for your
Thank you.
thank you. Thank you, sir. So, participants, just I want to make you one small announcement. How many have completed the yesterday's hands-on practice? Is it clear over? Just I will unmute all. You please, you can, or otherwise the participants can type on your chat box yes or no. How many have completed? All it is clear, no? That is whatever the hands-on you have done yesterday on Intel suit, Intel suit thing. Hello, participants, are you there or not? Okay. Um, yeah. So, today also we will continue 1 hour. Just I want to add one more topic on that computer vision by someone request. Is it okay or it is? Just I want to inform you then. Okay. So you be once again we will meet uh, at uh, at 3 o'clock. Once again we will meet at 3 o'clock. Okay, then we will leave for today's session. Okay, so then bye. We'll have a break for lunch break from 2 to 3, and we will back by 3 o'clock.